Okay, good morning and happy Monday. So let's move back to wastewater treatment. We had been looking at primary treatment and we were talking about bar screens. So what you see here is the bar screen. Water can flow in either direction here. And notice we have the sluice gates here so that we can isolate the channel. And that's because the bar screens have to be periodically cleaned. Either they're typically mechanically cleaned routinely, but often this channel has to be cleaned out. So we want to be able to isolate that channel so that we can do the cleaning. And you can see here a stop plate or a slide gate. And notice here we've got these fillets in the corners, and that's just to try and prevent the accumulation of solids along the edges of the channel. So typically from the bar screen, the water flows into a grit chamber. And the purpose of the grit chamber is to remove any inert, dense material. So sand, broken glass, gravel, silt, petals, coffee grinds. The amount of material that is removed is very much dependent on the extent to which the sewer system is a combined sanitary sewer and storm sewer. The more storm sewer that's present, then typically the more grit that you have present. These typically have to be cleaned manually or mechanically. And if they're cleaned manually, then there needs to be storage space for the deposited grit. And you see the grit here in this image here. So it's a fine material, slightly larger typically than coffee grinds. It is actually most plants that I've been in, it is the smelliest part of the plant. Typically, it contains organic matter, and that organic matter can go septic quite quickly. So that creates odors. Some facilities will have a washing procedure so that they wash the grit, and then the wash water from that grit goes back to the headworks of the plant. The goal of this is to remove this inorganic material, the solid material, but keep the organics in suspension. So typically there's often a rotational flow in here. You can see that they're aerating this device, and that's to try and attempt to keep this organic material in suspension. And it's not uncommon that these are aerated devices. That the grit is then typically disposed of in a landfill. And you can see here's a image of a grit chamber. It operates similarly. This is a horizontal grit chamber. It operates similarly as a primary sedimentation basin, although the detention time in these typically is much less. It's typically only about 10 seconds to 1 minute with a velocity of about 1 foot per second. So a detention time of 10 seconds to 1 minute. So that's much less than in a primary sedimentation basin. And you've got the scraping device at the bottom, again, to try and gather that grit, in this case, in a location that then can be removed. Following the grit chamber, The water often then flows into an equalization basin. So here you're looking at equalizing both the flow and the strength. And this is just a figure showing you the variations in flow to a wastewater treatment plant. Slowest at night, increases in the morning as everyone wakes up, takes showers, prepares for the day, and then typically will increase again in the evening when people are home. Now, equalization also attempts to equalize the strength of the waste because your BOD levels will be an inverse of this. So if we look at BOD and that as a measure of strength, it typically will be the exact opposite. So the highest strength in the middle of the night, lowest strength in the morning, and then kind of some oscillation during the day. Often, aeration is accomplished in these equalization basins, and that's to, one, try and keep the suspended solids in suspension. You don't want that wastewater going septic, so you don't want it to be devoid of oxygen. With aeration, you will get some reduction of BOD because you'll actually get some microbial activity. City of East Lansing had an equalization basin. It was an underground basin. It was under a parking lot. It was a serpentine basin. They recently took that out of commission. And they had some real problems with this system. As I've mentioned before, the sanitary wastewater that is treated at the City of East Lansing's plant comes all the way from out on the eastern side of Okemos. So it's got a long tension. It is often septic, and they had significant problems with corrosion of the aerators in this underground tank. So they actually shut off aeration because they had trouble maintaining it. And then they also had significant problems because it was this serpentine tank with sedimentation especially in the areas. If this is our tank and it's serpentine, so we have water coming in here, flowing this way, and eventually out. As that water turns, it slows, so they'd have significant deposition, especially in the corners. And as you can imagine, this being an underground tank, this is confined space. Somebody has to go in and clean this, and it was just more problems than it was worth. So they actually took that offline. But some plants still do use equalization. Everything we've talked about so far is considered primary treatment. So the goal of that primary treatment is to remove the inorganic material, protect the pumps, equalize the strength and flow entering the rest of the plant. From there, it moves into the primary sedimentation basins. The goal of primary sedimentation is to remove suspended solids. So typically, it will remove about 30 to 35% of the raw sewage BOD. The BOD that it's removing here is attached to particulates. So it's attached to these particulates that are being removed. And then it removes typically about 50 to 60% of the suspended solids. These are the primary sedimentation basins at the East Lansing plant. They're horizontal sedimentation basin. You can see the scum on the top. This is the oils and grease. You can see this is the scum trough here. And the goal is to skim that off at the top. The solids are settling to the bottom. This is a horizontal sedimentation basin, and I'm going to switch to a video to give you a better sense, but this is that chain and flight mechanism here. So you've got this flow traveling in this direction here. You have a hopper that collects the sludge, and periodically that sludge pump will turn on and pump that to the treatment for the sludge. And we'll talk about that hopefully on Friday. And then we have often a scum trough. You can see that here. So we've got a scum trough, and any of that, the oils or grease, floating material, then gets pushed into that scum trough. And we have the influent and our effluent on opposite ends of the tank. So let's just take a look at this video.
Wastewater is then piped into long primary tanks and slowed. Here, fats, oils, and grease float to the top, and heavy solid material sinks to the bottom. Large fiberglass bars push the floating particles into troughs and continue on a circular path to the bottom of the tank and scrape the settled material out of the tank.
So hopefully that little video gave you some little better image of what is happening here and how this chain and flight mechanism actually is working. This is a circular clarifier, essentially works the same way. Here, the sludge is scraped into a center trough. Again, there is a surface skimmer. In some cases, there's actually a stream of water that is sprayed onto the skimmer to try and push the one, to keep it clean, and to push the scum into the skimmer. And you can see the same. This is, in this case, the upper is a center feed. So the water is distributed from the center. The bottom is a peripheral feed. So you can see the influent here is on the edge and along the edge of the basin. And then you have the effluent. So let's do a little problem here. Very similar to what we have done before. And we have a situation where we're given the design flow. We're told that the influent suspended solids is 280 milligrams per liter. We have a sludge concentration of 6%. We actually don't need that. An efficiency of 60%, so that's how much suspended solids we are removing. And you have a length of 40 meters, a width of 10 meters, a liquid depth of 2 meters, and a weir length of 7 meters. So typically, we're looking at these systems. At average flow, our overflow rate typically will be between 25 to 60 cubic meters per meter squared per day. And at peak flow, 80 to 120 meters cubed per meter squared per day. Typical detention times are 1.5 to 2.5 hours. So in terms of the calculations, these are identical to what we've done before. Our detention time is simply the volume divided by the flow rate, and that is 40 meters by 10 meters by 2 meters divided by our flow rate, and that is 5,333 seconds or 1.5 hours. It's right where we want to be with. The overflow rate is our flow rate divided by the surface area, which is 40 meters by 10 meters, 86,400 seconds per day, times that. And that is 32 meters per day. And if you remember, we could also calculate the overflow rate as the height divided by the detention time. And that is 2.0 divided by 1.5 hours divided by 24 hours per day. And that is the same 32 meters per day. Should be. And we've just shown that that is the case. And this is right within the range for an average flow rate. The weir loading is our flow rate divided by the weir length, and that is 173 meters cubed per meter a day. And our weir loadings should be less than 250 meters cubed per meter per day for typical flow rates. So, and that's at average flow rate. So we've met the weir loading. So we've got so now we've gone through pre-treatment, primary treatment, and now we move into secondary treatment. Secondary treatment has an objective of the removal of soluble BOD. Everything here is focused on suspended material. So it's focused on removing that large material, the twigs, the rags, the toys that got thrown down the toilet and flushed down the toilet. In the bar rack, it is focused on removing inorganic material in the grit chamber, and then on suspended solids in the primary clarifier. There will be additional removal of suspended solids in biological treatment, secondary treatment, but the objective, the whole design is based on removal of soluble BOD. We will use microorganisms to do that. The goal of secondary treatment is to accomplish what normally would happen in a body of water, but happens over a much longer period of time. Typically, if we look at the dissolved oxygen concentration in a body of water, it is relatively constant, and then we think of adding some sort of a municipal wastewater. This wastewater has organic material that consumes oxygen. So BOD5 is how we typically describe this. You see a decrease in dissolved oxygen levels. It reaches some minimum. Here shown as 2 parts per million. It can be lower than that. It can be mathematically, our models will show a dissolved or achieve a dissolved oxygen level that's negative. It really means that it is 0. So yes, it can be below 2. It could be less than, or much greater than that, depending on the strength of the waste. If the wastewater consumes too much oxygen, then we can end up with a septic zone. And there you see fish kills. You see a proliferation of these little organisms, tubifex, which are known as sludge worms, and midgefly larvae. So it changes the ecosystem, and then we have a recovery zone. What we want to do is we want to use the microorganisms so in the treatment plant in a engineered system so that this doesn't occur. What we have is something much more like this, where in the environment where we're not depleting oxygen. So we're going to use a suite of microorganisms to convert that organic waste into stabilized compounds. So we're looking at converting organic waste into CO2, nitrate, or if we have denitrification, all the way to nitrogen, any sulfur to sulfate, and we'll talk a little bit about phosphorus and how we deal with phosphorus in the water. So in terms of operation of these systems, we need to make sure that we have a high density of microorganisms. The density of the microorganisms is much greater than what you would see in a body of water, a natural body of water. We want to have good contact between the organisms and the waste, and we're really looking at the organic matter in the waste. Have organic matter. We also need to provide a favorable temperature, pH. We need to provide nutrients. We need to have a carbon source, so we need to have food for the microorganisms. And we need to make sure that we don't have any toxic chemicals present. We talked about pre-treatment requirements. This is why we need the pre-treatment requirements. Now, when we talk about biological growth and secondary treatment, we talk about it in terms of both dispersed growth and fixed growth. So dispersed growth, the microorganisms are dispersed within a treatment system. This can be an activated sludge system, it can be oxidation ditches. We'll go through and look at these. It could be an aerated lagoon or a stabilization plant. Fixed growth means we have some sort of a solid support, and we have the microorganisms on that solid support, and the water flows past those microorganisms. And as the water flows past those microorganisms, there's diffusion of the organics into this biofilm here and degradation of the organic matter. So these are the aeration tanks at the East Lansing wastewater treatment plant. They're deep. What you have is these are the oxygen diffusers. So you're adding typically air in these diffusers. You're aerating the system. These operate as they're very long serpentine system. And the water's held in here for 8+ hours. And in that period of time, the microorganisms consume the organic matter. The system involves both an aeration tank here and a secondary clarifier. So we're adding oxygen along this aeration tank. This X is our mixed liquor, volatile suspended solids. So it's mixed liquor, volatile suspended solids is the term we'll use. That quantifies the concentration of microorganisms. S is our substrate. That's the BOD. So that's the amount of organic matter that can be consumed by the microorganisms. V is our volume. Now, notice we have a return line here. what we're doing is we're recycling the microorganisms. These microorganisms are useful. So we need to keep and maintain those to maintain this high concentration. So what we'll do is the water from the aeration tank flows into a secondary tank. So notice we have Q. So this is the Q from the primary settling tank. We have a return flow rate. So this is what's coming from the bottom of the secondary clarifier. So this is our effluent here. This is our settled secondary sludge. Some of it we will waste, and some of it we will return back to the primary tank to maintain this mixed liquor volatile suspended solids concentration, to maintain a concentration of microorganisms in the activated sludge tank or the aeration tank. So we'll go through a number of these processes, these calculations, but number of things I want you to note from this, okay? What we will be doing is a mass balance around the secondary clarifier. So going back to here, notice this line, the dotted line here. This is our system boundary. What then we will define this as, okay? We have a flow in, we have a flow out from our effluent, and we have a flow from the waste activated sludge. Notice everything else is within the system boundary. So our mass balance will not include this internal loop here. It only includes the waste. We need to define, though, this mixed liquor suspended solids concentration. This X here is the biomass concentration in the aeration tank. And it's a function of how long the solids reside in the tank. So notice we're recycling these solids. So the solids will stay in the tank longer than the water does. It is a function of this yield coefficient. And this is the amount of biomass that we're producing per mass of BOD we're consuming. So think of it as basically the efficiency of organic matter usage. Our hydraulic retention time is the same. So this is just our detention time. S0 is the influent BOD concentration that's coming from the primary tank. And this S sub E is the effluent concentration. Actually, we will make the assumption that there is no BOD removal in the sedimentation tank. Our mass balance here, notice this includes our flow, our recycle flow, our wastewater flow, this E here. So this is what enters, okay, and this is what's leaving. And we're assuming steady state. So accumulation is equal to 0. So this is in. This just gives you an indication of the various different design parameters. We will focus our discussion here on completely mixed reactors. So notice here, typically you're looking at about 4 to 15 days that the microorganisms are being recycled. We talk about a food to mass ratio. So that is the mass of BOD per mass of MLSS, mixed liquor suspended solids. So it's the mass of BOD actually per day. So it's if we're looking here at a reactor, so it's the mass per day of BOD that's entering divided by the mass of the mass of mixed liquor suspended solids, MLSS, in the system. The volumetric loading is the mass of BOD per volume of the reactor. Notice your hydraulic residence time is only about 3 to 5 hours compared to a mean cell residence time of 4 to 5 days. Your mixed liquor suspended solids is about 3,000 to 6,000 milligrams per liter. When we talk about microorganisms in in a natural environment, we're talking about number of organisms, for instance, red cedar, maybe less than 200 organisms per 100 milliliters. So much less than what you'd see here. I mean, that's a number of organisms, not milligrams. The recycle ratio is 0.25 to 1. So this flow rate back here, okay, if we take Q sub R over Q, ranges from 0.2 to 1. So you can have a significant amount of flow. If it's 1, then this volume is twice what it would be based on this Q, the initial Q. This is a completely mixed reactor. Typically, we would achieve 85 to 95% removal, and this is just how much air. The amount of air doesn't matter whether it's a plug flow reactor or a completely mixed reactor. We'll focus on this in terms of the actual design. So I've got a problem here. We'll start this on Wednesday rather than starting it now.
In the denitrification process, we convert nitrate to nitrogen gas. Nitrate is dangerous to the wildlife where the water will flow after it leaves the plant. So it's very important for us to take that nitrate out of the water and convert it into nitrogen gas. This is the main step of our biological treatment process. During this process, we don't use any chemicals. From this point, we're going to go to our next step, which is the secondary sedimentation tanks. This treatment process is called secondary sedimentation. This is just like primary sedimentation, but the bacteria that's in the water sink to the bottom very slowly. As you can see here, the water will overflow the weirs and then go on to the next treatment process. Anything that doesn't go over the weirs settles to the bottom and is reused and recycled into the aeration system. As you can see, we have our local wildlife that enjoys our secondary sedimentation tanks also.
Okay, we're back to here. I just wanted to give you a sense of the plan. Let's end here, and we will pick up with this problem, Gatesville, on Wednesday. And